All right, let's talk about calculus. And more specifically, let's talk about that first big roadblock that so many of us hit, limits. It's this abstract, kind of frustrating concept, right? But what if I told you the reason it's so tough isn't what you think? Today, we're going to demystify one of the most important ideas in all of math.
So, if you've ever found yourself just staring at a page, thinking, I just don't get it, well, you are definitely not alone. It's a universal struggle. But here's the good news. Figuring out why it's so hard is actually the first big step to finally mastering it. A recent study actually dug into this, analyzing student mistakes on limit problems. And what they found was pretty fascinating. Just look at this breakdown. Almost 68% of all mistakes, they're not from bad arithmetic or forgetting a rule. They're conceptual errors. And that tells us something huge. The real struggle isn't with the calculation, it's with the core idea itself.
Okay, so if the biggest problem is conceptual, what in the world does that actually mean? Let's break it down and look at the anatomy of one of these mistakes. Think about that number for a second. More than 2/3 of all errors. This is proof that the struggle isn't about being bad at math. It's about a disconnect with the fundamental idea of what a limit even is. It just requires a totally different way of thinking. So here's what it boils down to. A conceptual error means you don't really get the why behind the how. You might know the steps you're supposed to follow to solve a problem, but you don't truly understand why those steps are necessary in the first place.
And this slide just illustrates the point perfectly. Over on the left, you see the correct way to factor the expression to solve the limit. But now look at the handwritten example on the right. That is a very, very common error. But the key thing here isn't just that the algebra is wrong. It's this. This is the crucial point. A student might know they're supposed to factor, but they don't get that the whole goal is to eliminate the part of the fraction that's causing that 0 divided by 0 issue. It's like following a recipe without understanding any of the chemistry. That's the conceptual gap we're talking about.
So, why are these conceptual gaps so incredibly common? Well, to find the answer, we have to go right to the source code of calculus, the formal, official definition of a limit. And I'll give you a fair warning, it can look a little intimidating at first.
And there it is, the infamous epsilon delta definition. This is the rigorous logical foundation for every single limit you will ever solve. And if you're looking at that and thinking, what on earth does that even mean? Well, that's exactly the problem. This abstract language is ground zero for all the conceptual confusion. But don't worry, we're not going to get lost in all those symbols. We can actually translate this whole thing into something much more intuitive. Let's try thinking about it like a game of archery, where the goal is to prove you're an infinitely precise archer.
Okay, stay with me here. The limit, L, that's the bullseye. Now, your friend challenges you with an incredibly small target area around that bullseye. That's epsilon. Your job is to find a range of distances you can stand from, that's delta, so that no matter where you shoot from within that range, you are guaranteed to land inside that tiny epsilon circle. The proof of the limit is showing that no matter how ridiculously small your friend makes that target, you can always find a shooting range to match it.
And now we get to the aha moment. Let's see how this whole archery analogy explains those common conceptual errors we were just talking about. This is where it all clicks together.
On the left, that's the trap so many of us fall into, thinking a limit is just about plugging in a number. But that's what gives you 0 over 0, an undefined mess. The formal idea on the right is a completely different game. It's not about arriving at the point. It's about proving you can get arbitrarily, infinitely close to it from either side. And all those algebraic tricks, like factoring, they're just the tools we use to build that proof.
So now that we've really diagnosed the problem, how do we fix it? Well, that same study that identified all the errors also looked at what strategies actually work for students. So let's look at the data. Here are the top-rated strategies that students use to improve. Consulting resources like notes and online tutorials, that comes in at number 1. But check out what's tied for second, working with peers and revisiting foundational concepts. This shows that true understanding comes from both seeking out information and reinforcing the basics, often by talking it through with other people.
So what are the big takeaways here? Well, for students, the message is pretty clear. Shift your focus from just memorizing procedures to really understanding why they work. Talk it out with your classmates. And for educators, it's about explicitly teaching the concepts behind the calculations, using things like analogies, like our archery target, to make these abstract ideas finally stick.
And that leaves us with a final thought.
perhaps the journey to mastering limits isn't really about becoming a better calculator. Maybe it's about fundamentally changing our perspective and learning to appreciate the beautiful, rigorous logic of what it truly means to get infinitely close to something without ever actually having to touch it.